In our previous video, we talked about how to write a recursive equation, right? So if we look at this table right here, we see we're adding 4 each time. So we take our previous term and we add 4 and we make sure that we have f of 1 equals 7 or some sort of starting term that allows us to know where our sequence starts. What if somebody said, well, what is f of 300? That would be pretty tricky to find using this recursive equation because we would have to know f of 299 in order to figure out what f of 300 is, because we'd have to do f of 299 plus 4. And that would take a lot of time to expand this table 299 times. That's where our explicit equation comes in. It allows us to write the equation and not be dependent on the term before it so that we can find terms like 299 or 300 fairly quickly without having to expand our table or expand our sequence that far. So the nice thing about writing an explicit equation for a linear or arithmetic sequence or table is you actually already know how to do that. In our previous videos, we talked about writing the equation y equals mx plus b. And this right here is the explicit equation for a linear function because it tells you any term you want just by plugging in the numbers for x and y. Think back to what m and b mean, right? This was our slope and this was our y-intercept. When we write an explicit equation for arithmetic sequence or table, we're just going to replace y and x with n and f of n, and then we're going to change m, which is our slope, to d, if you remember, was our common difference. And we already know what our y-intercept is. We can also call this f of 0. When n is 0, we get our y-intercept there. If we change out everything from our y equals mx plus b form and replace it with our n and f of n, then we'll have f of n is going to equal, instead of our slope or m, it's going to equal d, which is our common difference, d times n instead of x because we're using n, and then plus our y-intercept, which is f of 0. If we replace it with the numbers we know for this table specifically, we'll have f of n. We know the common difference is 4, so 4n, and you can write times n if you want, or you can just write 4 next to the n. That means the same thing. Plus, we know that f of 0 is 3, or so our y-intercept is 3. So this right here is how you write an explicit function or explicit equation for this specific table that we've been given. And we don't have to specify that f of 1 is 7 or f of 2 is 11 because this equation gives us enough information, and we can even find the 300th term if we wanted to. We could just say that f of 300, that tells me if n is 300, I want to know the 300th term of my table, it's going to be equal to 4 times 300 plus 3. So 4 times 300 is 1200 plus 3 equals 1203. And this would be my 300th term. It's a lot easier to find the 300th term with an explicit equation than it would be with recursive having to expand your table.
Now that we know how to write an explicit equation for linear arithmetic growth, let's talk about writing an explicit equation for exponential or geometric growth. A really common example where you will see exponential or geometric growth in everyday life is with finances. So let's say you start off with $100 in your bank account and somehow you've hit the jackpot and you are able to double your money every month. I go from 100, if I double it, that's my common ratio. My ratio would be 2. I would get $200 my next month, and then I get $400 my next month. Maybe you have a really epic interest rate or something where your money is just growing like crazy. Writing a recursive equation for this is pretty nice, right? Because we just take our current month and we take the previous month's balance and we just times it by 2. Not too bad, right? We just take it, multiply it by 2. What if I wanted to predict how much money I would have at the end of 20 months? I would have to figure out how much money was in my account at 19 months in order to figure out my 20th month. So that might be a little hard if I don't want to keep multiplying by 2 20 times. I'm going to expand off to the side here another way to kind of visually see what's happening, and we might be able to better write an equation. I want to be able to plug in 0 in for n and get out 100. Or if I plugged in 1 in for n, then I get out 200. Or if I plugged in 4 in for n, I get out 1600. So we're going to expand our table a little bit to kind of get an idea of what is going on here. So in order to get my next number, I have to multiply it by 2, right? So I take 100, I times it by 2, and that gives me 200. Another way to express 200 is 100 times 2. In order to get my next term here, I had to take my 200 and I had to multiply it by 2. Getting to 400 is the same as taking 100 times 2 and multiplying that by 2 again. Another way I could write 800 in terms of what came first first is 100, and then I times that by 2, then I times that by 2, and then I times that by 2. Okay, another way I could write 1600 is from the very beginning I had $100, and I multiply that by 2, then I multiplied that by 2, then I multiplied that by 2, and then I multiplied that by 2. I'm taking everything I had before, and I'm multiplying it by 2, right? Is there a shorter way we can write this? Okay, well, I see that I have a 2 here, and it shows up once. I have a 2 here, and it shows up twice. I have a 2 here, lots of 2s, and guess what? That shows up 3 times. I have 4 2s being multiplied here, and that shows up 4 times. So if I want to make an equation with n, I would take my first number, they all start with 100, which is f of 0. F of n would equal f of 0 times by 2, right? 2 is the one being repeated, and it's being repeated n times. We can see here that 100 is our starting value, so we have f of 0, and I'm taking my common ratio in this case, which is 2, and it's being multiplied however many times. So it's multiplied once here, twice here, 3 times here, 4 times here, and if I just want a general equation of n, then I'd say n times. So my equation here would be f of n equals f of 0 times 2 to the nth power. So I can figure out how much money I would have after 20 months if I did f of 20 equals f of 0 times 2 to the 20th power. This would be the same as 100 times 2 to the 20th power, which is the same as having $104,857,600 at the end of 20 months if my money kept doubling. So this was a lot nicer for writing my equation than trying to do the recursive form. If I just want my general form is, we do have a resource page that has the recursive and the explicit equations. Check out our resource page.
If we are given a list like this and we want to write an explicit equation for this sequence, we have to first decide, is this linear and arithmetic or is it geometric and exponential? If we look at our first term to our second term, I can see 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9. So I can see right off the bat that I'm adding 2 every time. So I'm going to go to this form right here. This is linear / arithmetic, so we are going to use this explicit function right here. So I'm going to start with f of n, and that's going to be equal to d times n, and in this case, d equals 2. This is my common difference. What am I adding or subtracting each time? 2 times n, and then I'm going to add f of 0. So the tricky thing about a list is when you're writing a list, the first number in your list is always your term 1. You're not going to start on your 0th term. That doesn't really make sense to have the first term be your 0th term. So if you're given a list, then you need to go back one more to figure out what your 0 is, because this is your first term, your second term, third term, fourth term, and so on. And we know that we want our 0th term in our explicit equation. So figure out what number goes here. Well, if I'm adding 2 every time, to work backward, I'm going to subtract 2, so this will be 1. And then I can check my work and make sure, well, 1 plus 2 does indeed give me 3. I know that my 0th term is 1. This right here would be my explicit equation. F of n equals 2 times n plus 1.
You may also see on your assignment where you are given the recursive form and you have to write the explicit form. So first off, let's identify whether this is linear, arithmetic, or exponential and geometric. So looking at this is saying my current term is equal to my previous term times by -3. So because I'm multiplying by -3, I know that this is an exponential or geometric growth because I'm being multiplied by a constant every time. It also gives me my first term in my list, which is 7. If I were to create a little list, I know my first term would be 7. My next number is multiplied by -3, so it would be -21. And multiplied again by -3, it would be 63. Multiplied again by 3, it would be -189. And so we can kind of see what the list would look like. Now let's turn this into our exponential or geometric explicit equation. I know we're going to start off with f of n, and that equals, I need to find f of 0. I know f of 1 is 7. I need to find the number that comes before it. So remember, if this way I am multiplying by -3 each time, I can easily go backwards if I'm trying to find the previous term by dividing by -3. 7 divided by -3 is just -7 over 3. Literally 7 divided by -3. So my f of 0 is -7 thirds. That's my starting term. And then I'm multiplying by r times r. My r value is the constant that I'm multiplying by each time, which in this case is -r equals -3. And I can put that in parentheses if I want to. And then I raise that to the n power. This is my explicit equation given this recursive form. You can always check yourself. You can plug in a point to see. So I know this is my 0th term, my first term, my second term, my third term. Sometimes they write it as a sub 0, a sub 1, or you'll also see it written as f of 2, f of 3. You can see it either way. But you can plug in a point to c. So if I want to test out 2, I can do f of 2. Does that equal -7 over 3, -3 the second power? -3 squared is the same as 9. So -7 over 3 times 9. 9 times -7 is -63. Divided by 3 is indeed -21. So I know that this explicit form worked. Let's hone in on exponential or geometric growth. Exponential growth is anything where the variable is in the exponent. So if I have something that looks like x squared, even though this has an exponent, I would say that this is not exponential growth because my variable is not the one that is the exponent. If I had another example like 1/3 to the x power, this one is exponential because my variable is the exponent. So whenever you have a base number that is an actual number and it's being raised to some variable, that is exponential. But if it's the other way around, like x squared, or maybe you have like y to the 7th power or something, this is not exponential because variable is not the exponent.